Number 6 in your package. So we saw that coterminal angles have the same terminal arm. They have the same stopping point as you rotate around the unit circle. And we saw that we can generate those by adding or subtracting multiples of either 360 degrees or 2 pi radians, depending on whether you're measuring the angle in degrees or radians. One complete revolution around the circle, no matter where you start, is 360 degrees, either in a positive or a negative direction, or 2 pi radians in either a positive or negative direction. So we can have the general form of a rotation angle. It's an expression containing parameters that can be given specific values to generate any answer that satisfies the given information or situation. It represents all possible cases. So any given angle that has an infinite number of angles coterminal with it, since each time you make one full rotation from the terminal arm, you arrive back at the same terminal arm. Angles coterminal with any angle theta can be described using this expression. Theta is plus or minus 360 n degrees, or theta plus or minus 2 pi n radians, where n is a natural number. This way of expressing an answer is called the general form. So it tells us to use this notation where n is a natural number. If you're using n as a natural number, remember natural numbers are positive counting numbers, including 0. Instead of using natural numbers, though, we can use integers, and then that eliminates the use of the plus and minus. Okay? So as I do these, I'm going to use integers, and so instead of these expressions, we will use these expressions here. Theta plus 360 n degrees, or theta plus 2 pi n radians, where n is an element of integers. By using integers, it eliminates the need for the plus and the minus after the theta. If you want to use natural numbers, that's fine, but you have to make sure you put a plus and a minus between theta and the angle. Okay? But I'm going to be using integers, which eliminates the use of the plus or the minus. So this first question says, express the angles that are coterminal with 110 degrees in general form. So that's the first part of this. Because that angle is 110 degrees, we're going to be using degrees, and we would say that the general form would be 110 degrees plus every multiple of 360 n degrees, where again, n is an element of integers. When n is negative 1, you're going to subtract 360 degrees. You're going to go 360 degrees in a clockwise direction. When n is negative 2, you're going to go twice around the circle in a clockwise direction. You're actually going to go 720 degrees from 110. When n is negative 3, you're going to go 3 rotations in a clockwise direction. And when n is positive 1, you go 360 in a positive direction, so you add 360. When n is 2, you'd add another 360, or you'd add 720 onto 110, and so on. Okay? So the second part of this is it says also to identify the angles that are coterminal with 110 degrees that satisfy that domain where theta is greater than or equal to negative 720, less than or equal to positive. So we want to identify all the angles that are coterminal with 110 that fall within that range between negative and positive 720 degrees. So if we start with 110 and we, let's say, subtract 360 degrees, that will give us negative 250. If you go negative 250 degrees or 250 degrees in a clockwise direction, you will end up at the same spot as if you went positive 110 degrees from 0. They are coterminal angles. They have the same terminal arm. They end up at exactly the same spot. If we subtract another 360, that gives us negative 610. So that would be another angle that's coterminal with 110 degrees. Okay, it had the same terminal arm, the same stopping point. And you should recognize that if you subtracted another 360, you'd be at an angle less than negative 720. So we wouldn't include that in our list of answers because we only want to state the angles between negative and positive 720. So negative 610, negative 250 would be our first coterminal angles. The ones that are negative. And it doesn't matter what order you write these in. I'm writing them from smallest to greatest. Now our next angle, we would not say 110 degrees. That's not coterminal with 110 because it is the same rotation angle. But we can get a positive rotation angle by taking the 110 and now adding 360. And again, we're using 360 degrees because that's what you have to do do one complete revolution around the circle. So that's positive 470. And if I add another 360, we're outside the domain. That angle is greater than positive 720, so we would only include that. We'd stop at positive 470. So there are only three angles coterminal with negative 110 between negative 720 and positive 720. We would not use 110 because it's not coterminal with 110, it is 110. To get a coterminal angle, you have to do a rotation around the circle. So this next one, now the angle is in radians. So if we want to state all angles coterminal with 8 pi on 3 in general form, we would say that theta is 8 pi on 3, which is in radians now. Whenever you have an angle expressed in terms of pi, that's radians. Or if there's no degree symbol, meaning no unit given, that's also radians. So here we'd have to add multiples of 2 pi because that's how many radians you have to go around to do one rotation in a circle, where again n is an element of integers. So there's the general expression for all angles coterminal with 8 pi on 3. And we also want to state all angles that are coterminal with 8 pi on 3 that fall within the domain of negative 4 pi to positive 4 pi. Now, our original angle has a denominator of 3, 8 pi on 3s. So to make things easier, I'm going to write my domain also with denominators of 3. This negative 4 pi is negative 4 pi over 1, same with the positive 4 pi. To write that with the denominator of 3, we multiply bottom and top by 3. So we would say this could also be negative 12 pi on 3 less than or equal to theta, which is less than or equal to positive 12 pi on 3. Because our angles are going to be expressed as multiples of pi on 3, we want to have our domain also written with the denominator of 3. So if you start with 8 pi on 3 and you subtract 12 pi on, I'm sorry, not 12 pi on 3. The other thing we're going to have to do here is we're going to have to remember that we are adding and subtracting multiples of 2 pi or 2 pi over 1, which would be 6 pi over 3s. We need a common denominator so that we can subtract these. So instead of subtracting 2 pi, we will subtract 6 pi on 3. So that gives us 2 pi on 3. That's one angle coterminal. And then we'll subtract another 6 pi over 3, which gives us negative 4 pi on 3. That one will work because it is within the domain between negative 12 and positive 12 pi on 3. If we subtract another 6 pi on 3, that'll take us to negative 10 pi on 3, which again is within that domain. Yes? Because that's the same as 2 pi. Remember, 2 pi is one revolution around the circle. But we need to write it with a denominator of 3 because we're starting with 8 pi on 3. So we need a common denominator there. And you should recognize that if you subtract another 6 pi on 3, you'd be at negative 16 pi on 3, which is too small. That is smaller than our negative 12 pi on 3 that we set as our domain up here at the top. So we're not going to go any further in the negative side, but we can see if we can go further in the positive side. If we take the positive 8 pi on 3 that we started with, and now we add 6 pi on 3, that's going to take us to 14 pi on 3. Can we use that, Dylan? Why? It's too big. Not in the domain. It's greater than 12 pi on 3, which is our upper limit here that we set. So we cannot use this one. We only have one positive, which is our 2 pi on 3, and two negatives. Negative 4 pi on 3, and negative 10 pi on 3. Those are the only ones that work for the specified domain that we are given. Okay? Now, what about, I guess that's it for that. We already did our general form for all angles, right? That's the first thing we wrote. That will cover every possible angle that's coterminal with 8 pi on 3. And then we had our specific ones that fell between negative 12 pi on 3 and positive 12 pi on 3, which is the same as negative 4 pi to positive 4 pi. So now let's switch gears a little bit and talk about the arc length of a circle. So we talked about the fact that the arc is a portion of the circumference, and we've talked about the fact that there's a relationship between theta, the central angle, which must be expressed in radians, the radius of the circle, and the arc length. And that relationship, one form of it is that the arc length equals r times theta, but the one that's on the formula sheet is that theta equals a over r, which you can get from that first expression by dividing both sides by r. But you have to remember when you use this is that theta must be expressed in radians. Theta must be expressed in radians. There's usually a question on the diploma exam where you have to use this formula in some form. Okay? Maybe you're going to be asked to find arc length given a radius and theta, but in most cases they will give theta in degrees, so you have to do the conversion first that we talked about last class. That's the most common type of question you're going to see, where you're going to be given theta, usually in degrees, you have to convert it to radians, and then you'll be either asked to find a given r or find r given a. And they must be in the same unit as well. Maybe both in centimeters, maybe both in inches, whatever the case is. Okay, so this next one is something that you would commonly see on a diploma exam because the central angle is given in terms of degrees. So Rosemary is taking a course in industrial engineering. For an assignment, she is designing the interface of a DVD player. In her plan, she includes a decorative arc below the on-off button. The arc has a central angle of 130 degrees in a circle with a radius of 6.7 millimeters. Determine the length of the arc to the nearest millimeter. So again, if we use the formula, you can either say that A equals r theta, which probably is a good one to use here because we want to find out what the arc length is. But again, the one on the formula sheet is that theta equals arc length divided by radius, which you could start with as well. Doesn't matter. But have to remember the first thing you must do is convert that angle from degrees to radians. So we said We saw this last class. To do the conversion, you're either going to multiply by pi and divide by 180, or multiply by 180 and divide by pi. To remember which way you go for this one, you also have to remember that the angle in radians as a number will always be smaller than the angle in degrees as a number. So if we're going to go from degrees to radians, our answer must get smaller, which means we're going to have to multiply by pi and divide by 180. That's the only way we're going to get a smaller answer than 130 degrees. If you multiply by 180 and then divide by pi, your answer is going to get larger. Okay, so in this case, I mean, you could write this as an exact value, which you'd want to do anyways for your calculation. You don't want to write this answer as a decimal that's rounded and then use that to find another answer. That's going to affect the accuracy of that final answer. Always use exact values where possible. So I divided top and bottom by 10 to simplify that. That's what theta is. And now we can say that A, the arc length, equals R, the radius, which is 6.7 millimeters, times theta, which is 13 pi over 18. So you could make the 6.7 over 1 to make it a fraction. Multiply top fractions is top times top, bottom times bottom. So we can go 6.7 times 13 pi. And I'm using the pi button here again because I want to have an exact value that I'm using in this calculation. So 6.7 times 13 pi divided by 18 will give us our answer, which it does say round to the nearest tenth. So now we will round approximately 15.2 millimeters. Okay. So there's that one. Example 5. A person on a Ferris wheel moves a distance from point A to B. The diameter of the wheel is 12 meters. The sector angle is 43 degrees. Calculate the distance from A to B to the nearest tenth. So in this case, again, we want to find A, the arc length. Remember, the arc length is a portion of the circumference. So a person in a chair of a Ferris wheel is going to be moving around along the outside of that wheel. That is arc length. And once again, we're given the angle in degrees, so we're going to have to convert that to radians. Also, the diameter is 12 meters, but the formula involves radius, which is half the diameter. So R, the radius is 6 meters. Theta, the angle in degrees, is 43, and we have to convert that to radians. So again, we're going to get a smaller answer than 43, which will only work if you multiply by pi and then divide by 180. And 43 is a prime number, so can't simplify that at all. So we'll leave it like that. And then we'll use the arc length formula, A equals radius times theta, the angle which must be expressed in radians, which we have. So it'll be 6 times 43 pi over 180. So, I mean, you could simplify this. You could put the 6 as 6 over 1. You could divide top and bottom by 6. That will leave you with 30 down there. So now we're at 43 pi over 30 as our answer. That's the answer as an exact value. And that would be in meters. But then it says round to the nearest tenth. So So 4.5. Would be the answer to the nearest tenth. So this next one, a circle with center C and a minor arc AB. So sometimes you'll see that terminology because technically if you want to talk about arc AB, you'd actually have two that you could look at. You could look at what's known as the major arc, which is the longest distance from A to B. That would be the major arc. Or the shortest distance from A to B. That is known as the minor arc, which is what we're given here. Okay, it's labeled where the 15.2 is. Also, the terminology minor arc means it's the shorter of the two. Okay, so that's the one that we're working with here. Then you're told that angle ABC, which is the angle you get by going from A to B to C. So there's angle ABC, that equals BAC, which is the angle at A. We're told that they are both pi on 6 radians. So this angle is pi on 6, and this angle is pi on 6. So we have the length of the arc, we have those two angles, we want to find r the radius. That's what we want to find, r the radius. To use the arc length formula, though, which again, the version that's on the formula sheet is that theta, the central angle, is the ratio of the arc length divided by the radius. We want to find out what the radius here would be. So we could take this equation and solve for r by first multiplying both sides by r. We would get r times theta equals a, and then dividing both sides by theta. So by doing a couple algebraic steps, we have r the radius by itself. But remember, theta is the central angle, which we are not given. We're given the other two. So how do we find the central angle? Vish. Okay, but those other two angles are not in terms of degrees. You could, but then you'd have to convert back after, because remember, to use the arc length formula, theta must be in radians. So you said that three angles of every triangle add up to 180 degrees. What would that be in radians? Pi radians. 2 pi is one rotation. Pi is halfway around the circle. So to find theta, we would have to take those two angles that were given and subtract them from pi. Three angles of a triangle always add up to 180 degrees, which is also pi radians. So I would write pi with a denominator of 6. That would be 6 pi over 6 minus 2 pi on 6's leaves us with 4 pi on 6's, or 2 pi on 3's. There's the measure of the central angle. The angle at C would be 2 pi on 3. So now r the radius can be found by taking a the arc length, which is 15.2 centimeters, and that is divided by 2 pi over 3 radians. You're dividing by a fraction. That's the same as multiplying by the reciprocal. So you're going to multiply by 3 over 2 pi. And I mean, you don't have to do that step, because you could take your calculator and go 15.2 divided by, in brackets, 2 pi over 3. Do it that way and get the answer, or 15.2 times 3 divided by 2 pi. Now, something's going on here. Divided by 2 pi over 3. Oh, I know why. You got to put the 2 pi in brackets, because otherwise your calculator will divide by 2 and then multiply that answer by pi. So the 2 pi must be in brackets if you do it that way. There we go, same answer. So the nearest tenth of a centimeter would be approximately 7.3. Approximately. Okay, so let's go on to page number 13. We've talked about the unit circle. We have talked about how we can label all the points along the unit circle. Multiples of pi on 2, pi on 4, pi on 3, and pi on 6. So we've done that part already. So now let's talk about what happens at each stop. We're going to see at each stop, you're going to get a set of coordinates, starting with the coordinates at the multiples of pi on 2. Because the unit circle is a circle with a radius of 1, this point here, where the unit circle intersects with the positive x-axis, has coordinates 1, 0. From the origin, you're going to go 1 unit to the right. You're not going to go up or down. Where the unit circle intersects with the positive arm of the y-axis, the coordinates there are 0, 1. Where the unit circle intersects with the negative part of the x-axis, it's -1, 0. And at the intersection with the negative part of the y-axis, it's 0, -1. So those are the coordinates there. And again, they actually mean something. So we're going to learn about what those mean. And we're also going to, through some work with special triangles, we're going to label all the other stops that we talked about before on the unit circle. So those multiples of pi on 4, those multiples of pi on 3 and pi on 6. We're going to have a set of coordinates for each of those stops all the way around the unit circle, and then we're going to see what they actually mean. But first, you can find the equation of the unit circle by using Pythagorean theorem. Remember that if you have a right triangle, which you have here, okay, where the terminal arm, which because it's a unit circle that has a length of 1, it forms a right triangle when you draw a line from P, which is the end of the terminal arm, perpendicular to the x-axis. So that's where A comes in. From point P, where it's the end of the terminal arm of the unit circle with a radius of 1, you draw a line perpendicular to the x-axis, you get a right triangle there. So to get to this point P, you'd have to go x values to the right and y value up, y units up. And we know that when you have a right triangle, Pythagorean theorem says that a squared plus b squared equals c squared, where a and b are the two legs of the right triangle, c is the hypotenuse. So the two legs of this right triangle would be x and y, so x squared plus y squared equals, and the length of the hypotenuse here is 1, and 1 squared is just 1. So this is the equation of the unit circle. And that's where the hypotenuse is 1. Then it says determine the equation of the circle with center at the origin and a radius of 2. Notice they didn't use the word unit circle here because for it to be the unit circle, the radius has to be 1. But you can still write the equation of any circle centered at the origin by using Pythagorean theorem above. It'll be x squared plus y squared. And instead of saying c squared, let's say r squared, because c represents the radius of that circle. And in this case here, the radius is 2, so it'll be x squared plus y squared equals 2 squared, which is 4. Thanks very much. This next example says determine the coordinates of all points on the unit circle. So now we're back to a unit circle, which means the radius is 1. That satisfy the conditions given. Draw a diagram in each case. So the first one is that the x-coordinate is positive 2/3. Remember that the unit circle is a circle with a radius of 1. So that means to get to this point here from the origin, you'd have to go 1 unit to the right, no units up. So the coordinates of that point is 1, 0. So to have an x value of 2/3, it would be approximately right there. 2/3 the distance from 0 to 1. And if that's what the x-coordinate is, then the terminal arm would intersect the unit circle approximately there, or down below here. These two terminal arms that I'm about to draw would have an x value of positive 2/3. So the coordinates there would be 2/3, comma, y, and in that case, the y value would be positive. But in the fourth quadrant, the y value would be negative. And remember, this is a unit circle, so therefore, the radius is 1. And if we draw lines from P, the point where the terminal arm hits the unit circle, if we draw lines perpendicular to the x-axis, we've got two right triangles formed there. One of them in quadrant 1, the other one in quadrant 4. So therefore, we can use Pythagorean theorem to find the missing value. In this case, those missing values will be what the y value is. It'll be positive in quadrant 1, it'll be negative in quadrant 2. And we can find out what it is again by using Pythagorean theorem. We know that x squared plus y squared equals r squared. Our x value here is 2/3. And because again it's a unit circle, r the radius is 1. When you square 2/3, you're going to get 4/9 plus y squared equals 1. And we need to solve for y. So we would subtract the 4/9 from both sides to get y squared equals. So on the right, if you subtract 4/9 from 1, we would want to write 1 with a denominator of 9 as well. It'll be 9/9. Whoops. Minus 4/9. So y squared will equal 5/9. And to get y by itself, you take the square root. And when you're solving an equation and you take the square root of both sides, there's always two answers, the positive and the negative. So it'll be plus and minus root 5 over root 9, which is 3. So there's the two y values. The y value in quadrant 1 will be the positive root of 5/3. And in quadrant 4, that'll be the negative root 5/3. Yes, Fish? 1. You're going 1 minus 4/9. You need a common denominator to subtract. You're subtracting 4/9 from 1. So you need a common denominator to do that. Okay? Question B. In this case, we're going to see there's only going to be one answer. We're given the y coordinate to be negative 1/√2, but we're also told that we're only in quadrant 3. So in the last one, we weren't told specifically what quadrant we were in, so therefore there were 2 possible answers because there are 2 quadrants where x is positive. But in this case, we're told that y is negative, right? Which means we could be in 3 or 4, but as soon as it says we're in quadrant 3, now we're only in, obviously, the 3rd quadrant. Remember, though, that the unit circle is a radius of 1. So this point over here would be negative 1 comma 0. Down here would be 0 comma negative 1. In this case, our y coordinate is negative 1 over root 2. So if you go negative 1 divided by the root of 2, that's negative 0.707. Negative 0.707 would be, I don't know, approximately right there. Approximately. So our rotation arm would hit the unit circle at the same height, approximately 0.707, but it's negative. Right? So approximately there. What we did before is we drew a line straight to the x-axis. In this case, we've got to go up to get to the x-axis. And that's where we get our right triangle from. We don't know what our x value is. That's what we need to find. Our y value is negative 1 over root 2. And again, because it's a unit circle, the radius is 1. We need to find out what our x value is. So when we set up our Pythagorean theorem, we will get 2 answers for x, a positive and the negative. We're going to use the negative one only here. X must be negative in quadrant 3 because we're going left from the origin. So again, we can find out what that x value is by using Pythagorean theorem. X squared plus y squared equals r squared. We're trying to find out what x is. Our y value is negative 1 over root 2. That needs to be all squared, and that equals r, which is 1 squared. Again, because this is a unit circle, the radius is 1. So when you square negative 1, you're going to get positive 1. When you square root 2, you're going to get 2. Again, we would subtract a half from both sides to get the x squared by itself. And 1 take away a half is a half. You could write 1 with the denominator of 2. It would be 2 over 2. Take away 1 over 2 still gives us 1 over 2. And now when you take the square root of both sides, normally when you take the square root of both sides and you're solving an equation, you're going to get a positive and a negative value. Positive and negative 1 over root 2. But like we said above, because you're only dealing with one quadrant in quadrant 3, to get in quadrant 3 from the origin you must go left, so the x value is only the negative. Negative 1 over root 2. In this case, it's the same as the y coordinate. They're both negative 1 over root 2. And we're going to see that happening here as we start to develop the unit circle. So that's our next step here. We're going to start labeling the points on the unit circle, and we're going to do that using special triangles. But before we do that, as we said, at every stop on the unit circle, you're going to get a set of coordinates. Right? Here, it's going to be 1, 0, where the unit circle intersects with the positive x-axis. Up at the intersection with the positive y-axis, it's 0, 1, because remember the radius is 1. Over here, it's negative 1, 0, and down here, it's 0, negative 1. Remember that this first angle could either be 0 degrees or 360 degrees. Could also be 0 radians or 2 pi radians. At the top, if we talk about this in terms of radians, that would be pi over 2 radians. Over here, we could say that's pi radians, halfway around the circle. And down here, we could say it's 3 pi over 2 radians, or 270 degrees if we wanted, just like pi radians is 180 degrees. But what do those numbers mean? Well, let's take our calculator and let's see what mode we're in. Right now, I am in radian mode, so let's stick in radian mode for now. And let's look at up here where we have a rotation angle of positive pi on 2, and we've got these two numbers here, 0 and 1. Let's say we take the sine of pi on 2 radians and see what we get. We get a value of 1. The sine of pi on 2 is 1. And if we put our calculator into degree mode and did the sine of 90 degrees, we'll get the same answer, positive 1, which, notice, that's the y value at this point. Okay? When we take the sine of pi on 2, we get an answer of 1, which is the y value up there. What if we do the cosine of pi on 2? And again, I'm using pi on 2 because I'm in radian mode. We get an answer of 0, which is the x value at pi on 2. So the 0 is the cosine of this angle. The 1 is the sine of that angle. Let's check pi radians now and see what happens, right? So if we take the sine of pi, again, we get the y value at pi radians on the unit circle. And if we take the cosine of pi, once again, it gives us the x value at that stop on the unit circle. So the same thing that happened at pi on 2 radians. Let's check at 3 pi on 2 and see if the exact same thing happens, only this time, let's go back to degree mode. So if we take the sine now of 270 degrees, which is what 3 pi on 2 radians is at the bottom. Once again, we get the y value at that stop. And if we take the cosine of 270, we do in fact get the x value at that stop. So now we see what these coordinates mean at every stop on the unit circle. At every stop on the unit circle, we're going to get a set of coordinates, an x value and a y value. Now we see that the x value tells you the cosine of the angle, where the y value tells you the sine of the angle. It worked for pi on 2 radians, it worked for pi radians, it worked for 270 degrees. It will also work for 0 degrees or 360 degrees. We can try those both because we're in degree mode. The sine of 0 is 0, which is the y value there. The sine of 360, which is coterminal with 0, is also 0. The cosine of 0 equals the cosine of 360. They are both positive 1, which is the x value at this stop. So again, at every stop on the unit circle, we're going to get a set of coordinates. The x value tells you the cosine of that angle, whereas the sine tells you or comes from the y value at that stop every single time. And you might be wondering, well, why do we need to know this? Because our calculator just gave us those values. Well, you're going to see why we use the unit circle, because as we start to build this, you're going to see a lot of values that are irrational. So if you want an exact value, the calculator won't give you an exact value for some of these points, some of these stops, because some of the values we get here are going to be irrational numbers. So where do these come from? So we've got these special triangles here. These first two triangles are similar triangles. They are the same shape, but just different size. The same shape meaning the angles are the same. right? They're just different in size. So it doesn't matter which one we use here. Let's use the larger one. And this actually comes from a unit square. A unit square where each side is 1 unit long. That's where it comes from. A unit square where each side is 1 unit long. And then a diagonal is drawn in this square. So that's where the triangle that you were originally given came from. A diagonal is drawn in that square, and it doesn't matter whether you use the top right triangle or the bottom right triangle, those two triangles are identical. So we're just dealing with the bottom one here, where this is 90 degrees, this angle is 45, as well as the one at the top would be 45. You bisected the 90-degree angle. The 90-degree angle in the top right of the square and the 90-degree angle in the bottom left. Using Pythagorean theorem, we can find the length of the hypotenuse. Right? So from this triangle, we can find the length of the hypotenuse using Pythagorean theorem. A squared plus b squared equals c squared. A and b are the two legs of the right triangle, which are 1 and 1. When you square 1, you'll get 1. 1 plus 1 is 2. And then you'll take the square root of both sides, and c will equal root 2. So in this case, we're not really solving an equation. We're just using Pythagorean theorem to find the length of the missing side. Not solving an equation, so therefore there's no plus or minus. We just want the length of the hypotenuse, which is root 2 units. Now, 45 degrees, which is the same as pi on 4 radians, is right here on the unit circle, halfway between 0 and 90. 45 degrees is the same thing as pi on 4 radians. And using this triangle up here, we can find the sine and cosine of 45 degrees, which is the same as the sine and cosine of pi on 4 radians. Using SOHCAHTOA, the cosine is the adjacent over the hypotenuse. So if we're going to say we're going to work from that 45-degree angle there, the hypotenuse is always the side across from the right angle, right? If we're using this angle here, the side across from that is the opposite, the third side is the adjacent. So from this 45-degree angle, the opposite is 1, the adjacent is 1. If you use the top 45-degree angle, sure, the opposite and adjacent would switch around, but they're both still 1. So it doesn't matter which 45-degree angle we work from. And I'm going to start with the cosine because, remember, the first point, or the first number on the unit circle, we have a set of coordinates at every stop. We've seen now that the first number tells you the cosine of that angle. And cosine is adjacent over hypotenuse. The adjacent is 1, the hypotenuse is 2, so it's 1 over root 2. From the triangle, the cosine is 1 over root 2. And remember, at every stop on the unit circle, you've got two numbers, two components. The first one is the cosine of the angle. The second one is the sine of the angle. So from this angle, remember that sine is opposite over hypotenuse. That's the SO part of SOHCAHTOA. Opposite is 1, hypotenuse is root 2, so it's also 1 over root 2. So there we go. We filled in that first stop on the unit circle for pi on 4 radians or 45 degrees. They're both 1 over root 2, comes from this special triangle. And remember, this tells us that the cosine of 45 degrees or pi on 4 radians is 1 over root 2. And that just so happens that the sine is the same value, 1 over root 2. If you go to your calculator, and again, we are in degrees right now, if you do the cosine of 45 degrees, your calculator gives you a value that is an irrational number. It's a non-repeating, non-terminating decimal. But now we know where that comes from. It is 1 over root 2. If you go 1 divided by root 2 in your calculator, you get that same decimal. But the special triangle, the unit circle, gives it to us as an exact value, whereas your calculator gives it to you as a decimal that you have to round. But now we know where that comes from. It comes from the unit circle, a value of 1 over root 2. All right. We have two more stops here that we need to label. The first stop is 30 degrees, which is pi on 6 radians. The other stop here is 60 degrees, which is pi on 3 radians. And to get those values, that's where these other triangles come in. Now, these two triangles here are the same triangle. They're just one standing up, one's laying on its side. That's all the only difference between them. So let's just use one of them, okay? And these actually come from an equilateral triangle. So actually, let me do it this way. Let's use the one up top here. I think it'll be easier to see. It comes from an equilateral triangle. So remember, an equilateral triangle is where all three sides are equal in length and all three angles are equal in measure. So that's what I'm doing here. I'm extending the base and then adding that other side here. I start with an equilateral triangle where all three sides are 2 units long. And because it's an equilateral triangle, all the angles are 60 degrees. So 60 degrees down here, it's 60 degrees down there. The one at the top originally would be 60 degrees also. And then what we do is we drop a perpendicular bisector. From the top straight down to the base, it's a perpendicular bisector. So not only does it hit the base at 90 degrees, it also bisects the base. So each of these sides would be 1 unit long, half of the two. It also bisects the angle at the top, which was 60 degrees. So now the two angles are 30. Whether we take the triangle on the left or the right triangle on the right doesn't matter. They are identical. They have a base of 1 unit. They have a hypotenuse of 2 units. This angle down here is 60. The angle at the top is 30. Once again, using Pythagorean theorem, we can find what the height of this triangle is, right? So using Pythagorean theorem, we would say, again, a squared plus b squared equals c squared. A and b are the two legs of the triangle. We have one of those legs. So let's say that A is the base of 1. We're going to find out what the other leg B is. That would be the height of the triangle. The hypotenuse is 2. 1 squared is 1. And instead of saying B, let's just change that to an H now because that's what it represents. It represents the height of the triangle. On the right side, 2 squared is 4. If you subtract the 1 from both sides, H squared will be 4 minus 1, which is 3. And then H will be the root of 3. Again, we're using Pythagorean theorem to find a missing side of the triangle, so there's only one answer, the positive. We're not solving an equation. We're finding a missing side of a right triangle. So that is root 3 units. Okay? So, at 30 degrees, we're going to have two numbers here. The first number will represent the cosine of 30 degrees. The second number will represent the sine of 30 degrees. So, for 30 degrees, we're going to use this angle up here at the top. And remember, cosine is adjacent over hypotenuse. So from this angle 30 degrees, the hypotenuse is 2. The side across from that angle, the opposite side is 1. and the third side is the adjacent. In this case, it would be root 3. Again, SOHCAHTOA tells us cosine is adjacent over hypotenuse. In this case, that would be root 3 over 2. That is the value of the cosine. That will be the first number at 30 degrees or pi on 6 radians. The second number is the sine, and sine is opposite over hypotenuse. That's what the SO part of SOHCAHTOA tells us. So from 30 degrees, the opposite side is 1. The hypotenuse, again, is 2. So there's the coordinates at the first stop of the unit circle after 0. That stop represents 30 degrees or pi on 6 radians. The exact value of the cosine of 30 degrees is root 3 over 2. If you do that on your calculator, if you take the cosine of 30, it gives it as a decimal. It's a non-repeating, non-terminating decimal. It's an irrational number, 0.8660, and it just keeps going on forever. But now we see where that number comes from. As an exact value, that is root 3 divided by 2. Same decimal. But when you use root 3 over 2, that is the exact value of the cosine of 30 degrees, or pi on 6 radians. It is the exact value. The calculator gives you an irrational number, a decimal that doesn't repeat or terminate, so you got to round it. The unit circle gives us the exact value. Now, for the sine of 30 degrees, or pi on 6 radians, if I change my mode to radians, just to show you it works either way, and if you take the sine of pi on 6, which will be the same as the sine of 30 degrees in radian mode, because it's 1/2 exactly, your calculator will give you 0.5, right? Because it turns out that 1/2 is a terminating decimal. So your calculator will give you that value as an exact value, but not the cosine. Okay? So lastly, what about at 60 degrees or pi on 3 radians? So again, we're going to get two numbers here to give us our coordinate. The first number, the x value, is always the cosine of that angle. So if I want to find the cosine of now 60 degrees, I have to change around my opposite and adjacent. The hypotenuse doesn't change, right? The 2 is always the side across from the right angle. But now if you're working from the 60-degree angle, that's going to change the opposite and the adjacent. The side across from 60 degrees is the opposite. That's now root 3. The adjacent is 1 unit. So remember, the first number in the brackets is the cosine of the angle. The cosine is adjacent over hypotenuse. It'll be 1 over 2. Whereas the second number is the sine of the angle. The sine of 60 opposite over hypotenuse is root 3 over 2. It's the same two numbers from 30 degrees, just switched around. Instead of at 30 degrees where you have the root 3 over 2 first, the 1/2 second, at 60 degrees, it's the 1/2 first, the root 3 over 2 second. So you can use the unit circle to find the sine, cos, and cosine of every angle between 0 and 90 degrees where we stop on the unit circle. And those are multiples of 45 degrees, multiples of 60 degrees, or 30 degrees, multiples of pi on 2 radians, or pi on 4, or pi on 6, or pi on 3. You need to memorize this. Okay? You're expected to be able to remember what these numbers are. And it's not that hard to remember. I'm going to show you a couple tricks, okay, to remember them. One of them is that if we take 45 degrees or pi on 4 radians, right now They're both 1 over root 2. Well, we can rationalize those by multiplying top and bottom by root 2. So the sine of 45 degrees is 1 over root 2. And if you rationalize by multiplying top and bottom by root 2, you're going to get root 2 over 2. Same thing with the cosine. The cosine of 45 degrees, or pi on 4 radians, is also 1 over root 2. And again, if you rationalize by multiplying top and bottom by root 2, you'll also get root 2 over 2. So I'm going to go back and make those changes on the unit circle. And what this does is it gives all the denominators here the same value of 2. Okay? So let's make that change right now. This will be root 2 over 2, which remember came from the cosine. And this will also be root 2 over 2. The second number is the sine. All right? Okay. Here's how you can remember these. There's this hand trick. And if you Google hand trick for unit circle, you'll see this on Google. You'll see a video about it. A couple of them, actually. So I got my left hand out, my palm facing out. So this first finger, the little finger, would represent 0 degrees or 0 radians. The thumb represents 90 degrees or pi on 2 radians. So therefore, this next finger, your index finger, represents the first stop after 0, which is pi on 6 radians or 30 degrees. The middle finger, I know what some of you use this for, Diego. I'm not just looking at you. Actually, I am. But here, this represents pi on 4 radians, or 45 degrees. Therefore, this is 60 degrees, or pi on 3 radians. So here's how this works. If you want to know the cosine and the sine of 30 degrees, or pi on 6 radians, put that finger down. It's the root of this many fingers over 2, root of 1 over 2, which is 1 over 2, the root of this many fingers over 2, root of 3 over 2. So the top number gives you the cosine of the angle. The bottom gives you the sine. Okay? Sine is root 1 or 1 over 2. The cosine is root 3 over 2. Right? You just have to remember that it's cosine first, sine second. This actually gives you the sine. So it's this top number, top fingers, is the cosine, root 3 over 2, comma, root 1 over 2. So if you work from the top of your hand down, root 3 over 2 is the first one, root 1 over 2, which is 1 over 2, is the second one. For 45 degrees or pi on 4 radians, that's your middle finger. Root of this many fingers over 2, all the denominators are always 2, right? So this just gives you the numerator, the root of this many fingers, root 2 over 2, comma, root 2 over 2. That's what we have written down there. At 60 degrees or pi on 3 radians, it's the root of this many fingers over 2, root of 1 over 2, or 1 over 2, comma, root 3 over 2. So work from the top down, and it's the right order on the paper, on your unit circle. So you don't have to memorize them, right? It's always using the hand trick, you'll get them that way. But you have to make sure that you use your left hand and you face your palm out, and then you use the fingers. Okay, so it works, right, to remember what those are. So this gives us the sine and the cosine. But you can also use this to get the tangent, because we have a trig identity, and we're going to learn when we get into chapter 6, we're going to be talking about trig identities. And one of the trig identities that we're going to learn about and use is that for all values of theta, The tan of theta can be found by taking sine of theta divided by the cosine of theta. These points on the unit circle only give us the cosine and the sine. But we can find out what the tangent is as an exact value by going sine theta over cos theta. We can do that, right? So, at 1, 0, which is at 0 or 360 degrees, we can find the tangent of that angle by going sine over cos. Remember, sine is the y value, cos is the x value. So when you go sine over cos, you're going to go 0 divided by 1. 0 divided by anything is 0. So the tangent of 0 degrees or 360 degrees or 0 radians or 2 pi radians is 0 from the unit circle. So I'm in radian mode. So if I take the tangent of 0 radians, it gives me 0. Or if I take the tangent of 2 pi radians, because that is the same as 0 radians, it gives me 0. If I go up to 90 degrees or pi on 2 radians, sine divided by cos would be 1 divided by 0. Not even Vish can divide by 0. There's only one person in the world that can divide by 0. You know who that is? Chuck Norris can divide by 0. Yeah. He can also count to infinity. He's done it actually twice. And you know, when Chuck Norris does push-ups, he pushes the earth down. Okay. 1 divided by 0 doesn't exist. It's undefined. It's infinity. That's the tangent. If you try and take the tangent of 90 degrees or the tangent of pi on 2 radians, you get an error in your calculator. It doesn't exist. Unless your name is Chuck Norris, you cannot do it. All right. So what about the other angles? Well, looking at what we have at 45 degrees or pi on 4 radians, the sine and cosine are the same value. What's the tangent of 45 degrees or pi on 4 radians going to be? When you divide something by itself, what do you get? You get 1. That's the tangent of 45 degrees or pi on 4 radians. Because at that stop on the unit circle, the cosine and sine are identical. So when you divide them, you divide something by itself, you're going to get 1. All right, what about 30 degrees or pi on 6 radians? So you'd have to go 1/2 divided by root 3 over 2. Right? It's sine divided by cosine. So let's do this up here at the top. The tangent of 30 degrees or pi on 6 radians would be 1/2 divided by root 3 over 2. Sine divided by cos. And to divide by a fraction, we multiply by the reciprocal. Multiply by the reciprocal. The 2's will cancel, and you'll get 1 over root 3, which if we rationalize that is root 3 over 3. Multiply top and bottom by root 3 to rationalize. That is the value of the tangent of pi on 6 radians. So let me see if I can make some room here for this. So in black, it's root 3 over 3. If you take the tangent of pi on 6 radians or 30 degrees, and I will use pi on 6 here because I am in radian mode in my calculator. The tangent of pi on 6, the calculator doesn't give you an exact value, it gives you an irrational number. But now we know that where that irrational number comes from, it is root 3 over 3. Root 3 divided by 3 is that decimal. But the unit circle, if we use it, gives that value as an exact number. Don't have to round it. Calculator can't do that. Okay? So at 60 degrees or pi on 3 radians, again, we find the tangent by going sine divided by cos. So the tangent of 60 degrees would be root 3 over 2 divided by a half. Sine divided by cos. Again, to divide by a fraction, we multiply by the reciprocal. Again, the 2's cancel, but now you have root 3 over 1, or just root 3. That is the value of the tangent of 60 degrees or pi on 3 radians. So let's use degrees in this case. So we'll change our mode back to degrees. So I can use 60 degrees. It would still work radians if I kept it in radian mode and did the tangent of pi on 3. But I change it back to degrees. So the tan of 60 degrees, again, is an irrational number. It's a non-repeating, non-terminating decimal. So your calculator gives it to you as an irrational number that you would have to round, but now we know where that number comes from. That is the same as the root of 3. The unit circle gives it to you as an exact value. All right? So there's no hand trick for the tangent. You have to use your values from your cosine and sine to get the tangent values. But you can use the hand trick to get the cosine of sine. Cosine and sine. And you maybe just might remember the tangent values. But if not, you can get them from the cosine and sine, remembering that tangent is sine over cos. It's always y divided by x, because the sine is the y value, cosine is the x value. Okay? So, again, at each of these stops, we can label the sine and the cosine. So for this first one, we are at 45 degrees or pi on 4 radians. The sine and cosine, or the cosine and sine, are both root 2 over 2. And the tangent is sine divided by cos, root 2 over 2 divided by root 2 over 2 is 1. So again, the tangent of 45 degrees would be root 2 over 2, which is a sine, divided by root 2 over 2, which is the cosine. They're the same value. When you divide something by itself, you always get 1. If you just want the sine, well, that is the y value. It's root 2 over 2. This next one, that's the first stop in the unit circle. That is 30 degrees, or pi on 6 radians. So using the hand trick, put down your index finger. It's the root of this many fingers over 2, root 3 over 2, and then the root of this many fingers over 2, root 1, or 1 over 2. So those are the coordinates here. Root 3 over 2, comma, 1 over 2. To find the tangent, tangent of pi on 6, again, it is sine divided by cos, 1/2 divided by root 3 over 2. To divide by a fraction, we multiply by the reciprocal. The 2's cancel, and you'll get 1 over root 3, which is root 3 over 3 if you rationalize it. If you just want the cosine, that's the, root 3 over 3. I said that, but that's not what I wrote. Comes from the 1 over root 3. If you just want the cosine, well, that is root 3 over 2. That's the x value at the stop. And this last one is 60 degrees, or pi on 3 radians. So using the hand trick, that's the finger next to the thumb you're putting down. It's the root of this many fingers over 2, the root of 1, which is 1 over 2, comma, root of 3 over 2. It's the same numbers from 30 degrees, just switched around. And if you want the tangent of pi on 6 radians, or 60 degrees, again, it's sine divided by cos. To divide by a fraction, we multiply by the reciprocal. So we multiply by 2 over 1. The 2's cancel, and you're just left with root 3. That is the tangent of theta, root 3. Okay, I'm going to stop here. We'll pick this up again tomorrow. What I would like you to do is just some questions, not on the unit circle, but just dealing with what we talked about at the start with coterminal angles. So if we back up, some questions that you can do for practice here will be on page 176, questions 9, 11, A through F, 13, 14, A and C only. So I'd like you to work on those for today. We'll continue talking about the unit circle tomorrow. Okay? I will post these solutions to Google Classroom so you can check your answers. Again, there's a couple of you that still haven't handed in that review from transformation, so you got to get that handed in. Right? I'm going to be putting in, probably by the end of this week, if you haven't done it, or any of the other assignments, I'm going to start plunking in zeros. Doesn't mean you can't hand it in, but at least you'll see what your mark actually is currently. Okay? So if you got assignments that are outstanding, make sure you get those handed in.